Okay, welcome everybody. Today we're going to talk a little bit more about plasticity, and we're getting closer to the actual plastic process that we want to describe mathematically and build models and so on. So far we have just been working with elastic things and tensors and vectors and so on, just the fundamental stuff, just the tools for you to getting closer and get to know. So the outline today is we start with looking at failure and initial yield criteria. We start looking at the yield function and invariants connected to that one, and to working stress space, because now we're going into the principal stress space, and we're going to build models out of that. We need a new coordinate system. It's the Haig-Westergaard coordinate system. We're going to take a look at that one and how you can actually simplify your equations and so on with the use of that equation, coordinate system. Also symmetry properties, something called the Lode angle and meridian plane. Then we're going to look at some of the most common models. We start up with the simplest one, it's the von Mises model, which is the one that is mostly used for modeling actually today, especially in the steel area. The first plastic model that you get familiar with. Then we have another one called Tresca criteria. It's quite old model, but quite useful, still useful, especially for the steel area, steel material. Both of these are pressure insensible. But then we will go into the more pressure sensible models like the Drucker-Prager and the Mohr-Coulomb, which are the Mohr-Coulomb is the more advanced one for sand, concrete, rocks, and so on. And it's a good exercise for using all these invariant properties that you have for a model. And this lecture, this lecture will more or less cover chapter 8. It's the last part that you have to read for yourself about anisotropic yield criteria and the 4-parameter model. So the book is, of course, as I always say, the most important thing. This is more like a guidance for you for the reading and for the exercise. So we start up then with failure and initial yield criteria. So far in the course we have just been looking at this part here. This is the elastic modulus. And if you cross this point here, you will have permanent deformation of the material. And this can be either that you fail the material, or as we have in this case, this seems to be like a steel material, you will have hardening of the material. And I was talking about permanent deformation, because that's what the plasticity do to you. Plasticity, when you have plastic deformation, you will have permanent deformation. If this is a tensile test, you will have permanent elongation, and this is the plastic strain that you put in, that you get from this plastic process. So if this is a steel material, this is the initial yield condition, sigma y0. Then you continue to load the material. You will have hardening. This can be a linear or non-linear curve here. Then you suddenly stop at this point A, and then you unload it. And you see you have the Young's modulus E, which gives you the stiffness of the material. And when you unload from this position here, when it's fully unloaded, you have permanent deformation of your material. But you see this Young's modulus usually is the same, independent on where you stop loading. And in the next lectures, we will look at this process a little bit more closer, because you can have this hardening can occur in many different ways, and you can have isotropic hardening or something else that will deform the material in different ways, but also the unloading and when you meet the yield surface again will be different depending on what kind of hardening rules you have. But we'll go into that in the next lecture. Today's lecture will be more about this point, the yielding point and the failure point of the material. So it's the initial and first part for theory of plasticity. And we have some parameters here. Sigma y0 we call initial yield stress, and sigma f we call the failure stress. And large F, in this case it's dependent on the stress tensor, we call the yield function. I will show you later on during this lecture that it can be dependent on many different invariants. You can have different combinations also. And usually this function here is normalized. So if this function is lower than 0, the material is elastic. You haven't reached the yield limit. If it's above, it's plastic. And if it's exactly 0, you're exactly on the yield limit of your material. So we go into that later on. You can have different kind of behavior also. This can be good to know. If this is a steel material, usually you have the elastic part and you have the elastoplastic part, because it's not only purely plastic when you have hardening. You usually have elastic part also. But in this case, if you have a material which is, you have a flat response, the stiffness is, you don't have any stiffness in the plastic part. You will have a perfectly plastic material, or ideally plastic material, we call it. Usually this is more for theory. There are almost no perfectly plastic materials, but it's very good for theory and building models and so on. Usually you have some kind of hardening or softening behavior in your material. This is more for concrete models, where you have micro cracks and so on, which occur, and you have a softening behavior, especially if you look at the material in a continuum way. The micro cracks will be the softening part. You can also choose to model it with the cracks within, but it's more complicated. So this is the types you will have. You will have hardening material, you have perfect plastic, or softening behavior. This is more for the next stage of the course, but just to let you know how it works. So we look at the yield limit, and it's not so easy to find it sometimes, depending on what kind of material you have. Sometimes you may not see any yielding at all. Maybe you have just elastic behavior, and then you have fracture directly, especially in concrete and soil and so on. It's very difficult to see the yield limit. But as like an example here, I have looked at mild and medium strength steel. Usually you have this behavior. You have an upper yield point and a lower yield point. These come from the slip bands in the steel. Because initially when you reach the limit, you slip a little bit between the metallic layers, and then the stresses go down, if you look globally at the test, and then you increase the load. So this is a typical behavior of this type of steel. So here you have to choose when you model. Maybe you need to have them both, or maybe you take something in between, depending on how accurate you want to be with your model. You can simplify it, or you can try to reach them both. If you look at high-strength steel, you don't have this. Usually, you don't have this behavior. It looks like this. It's like a smooth transition from the elastic part to the elastoplastic part. And then you need to have a number instead. So usually you say when you have a difference of 0.2% from the original curve here, from the stiffness curve, from the elastic stiffness curve, you say that this is your yield limit. You just set the point. This is my yield limit for this material. Just to have some standard to know where you put it. So this is the typical models that you can, or the responses that you can see if you work with metals, for example. I guess you have seen this before. So, continue with the failure and the initial yield criteria. The yield function can be dependent on many things. For example, the principal stresses that you have, sigma 1, 2, and 3. So this can be the variables for your yield function. But another way of writing it is to use the stresses, the invariants that you have, and use them to control the yielding point. So these three together, the first, second, and the third invariant that you have for your stress tensor will control the behavior. And if you just recall what it looks like, this was the trace, this is the deviatoric part, and this will also give you the deviatoric direction in stress space. We also talked last time about coordinate invariant things, and this means that the function has the same form as it has. Independently how you rotate your coordinate system, it will take the same form. And this has to be fulfilled. In this case, it's the stress tensor that controls the yielding point, and you have this one is rotated, but this one takes the same form. It works exactly in the same way. Yeah. This one and that one. This is principal stresses. I got a question here where I have used single indexes here and where I have double indexes here. And this is just a way of expressing that you have principal stresses, because when you rotate your coordinate system, you have a certain rotation, you have principal stresses. You don't have any shear stresses. Then it's principal stresses for the system. That's what you have. It's like when you're solving this eigenvalue problem. This is what you find. You can find your principal stresses, and then you only need one indices. So it's the largest one, you say sigma 1, middle one sigma 2, and the smallest one sigma 3. And when you have the full tensor properties, you have double indices. Okay. Yeah, we had coordinate invariance, but if you have an isotropic material also, last time we discussed this relation is exactly the same. You have the same properties independently of your rotator system. But if you have them both, this must be valid. That the function in the rotated and the unrotated system is exactly the same. So this is just the criteria that you fulfill with the invariant and isotropic criteria. So in this case, this yield function is an isotropic scalar tensor function. This is also described in the book quite well, if you look at that. It's just the criteria for this yield function. Okay, I was in the beginning of the lecture, I told you that the yield function is dependent on, it can be dependent on principal stresses and invariance. This was for the stress. I1, I2, I3 is for the stress tensor, and J1, J2, J3 is for the deviatoric stress tensor. But you can combine them. This I1 can be combined with the first this is the first invariant for the stress tensor, with the second invariant for the deviatoric tensor, and the third invariant for the deviatoric tensor. But you can also write it like this: cos 3 theta. And this, you see here, just to recall your memory, J2 looking like this is the deviatoric part, and J3 will give you the direction in the deviatoric plane. But you can write it like this. This is a combination of J3 and J2, like this. And we call this one theta. It's the Lode angle. I will show you what it is actually. It's it will give you the direction in the deviatoric plane. I'll come back to that later when I show you the coordinate system. This is described in the book also. It's not so bad as it looks like. So if you look at this one, the yield function, the first invariant will give you the pressure dependency in the model. The second one will give you the deviatoric part. And the third one will give you the direction of the deviatoric part. So it's more or less a vector dependent criteria, the last one. This is a full description, mechanical description of a yield function. Von Mises, you will see later on, will only be dependent on J2. We call it J2 plasticity. So it's only the deviatoric part. So you can simplify it. This is a general description that you see now. So it's a full one that you need for rocks and soil and so on. We'll have a full description for that. Usually for steels you can simplify it a little bit better. But nowadays you can see also this Lode angle dependency coming in. You have the triaxiality. For example, if you have cracks and so on, in front of cracks, you have a lot of triaxiality depending on the thickness of the material. Then this Lode angle can be very important. Also, if you have anisotropic behavior of the material. Okay, let's look at this coordinate system. It's also described in the book, and you have a picture like this. This is what we call the principal stress space. You have a space, a coordinate system, where you measure your stresses. It's with principal stresses. You have sigma 1, like that, sigma 2, and sigma 3. Here we put the coordinate system. And origo here, when you have 0 stresses. This is totally unloaded. You don't have any stresses in any material point. Then you put the coordinate system. And if you look at this coordinate system, exactly in the middle, between the 3 axes, you have the pressure axis. This is what you see here. This is a normalized vector along the pressure axis here. And if you have loaded your material to a certain pressure, you call it this point N. You can put the plane here because on this plane you have your pressure point for this material point. For example, if you load something, you pressurize it and you share it maybe a little bit, you have different kind of loading. You will have your pressure point here at point P. So you need to describe with a vector from origo to this point P here. But another way of doing it is to put the plane exactly on point N here. And you put a new coordinate system here, exactly on point N. And this is the local coordinate system for your loading point. So you put it on N, then you have rho, which will be the distance from N to the pressure point. And on this plane, because this is a polar coordinate system, you have an angle. These 3 axes, sigma 1, sigma 2, and sigma 3, will be projected on this plane. So you have like this, sigma 1, sigma 2, sigma 3, and you have your point here. You put the plane on the pressure point, and then you find on this plane you will have an angle and a distance. This is how it works, the Westergaard system. So you can describe this one mathematically also. with the normalized vector n. You see here you have 1, 1, 1, 1, meaning that you have contribution from each axis here, and it's normalized, so you have the square root out of 3 here. C will give you the distance to point n from origo with the principal stresses that you have from the system. We can be described like this: I1 first invariant divided by square root out of 3, and the point ON, origo to n, is this one. You can find this one. And as I told you, you have a global system which is connected to this one, and you have a local one which is connected to the polar coordinate system on this plane that is in this position here. And you have this coordinate system. So it's a projected coordinate system in stress space. This will simplify your calculations quite much. And if you want to find the point NP here, you just take OP minus ON, looking like this, and maybe you recognize it. It's the principal stresses minus the trace of the stress tensor. Will give you the deviatoric part. So you will have a deviatoric plane in stress space. And the distance from this stress point N to pressure point N to your point P will be rho, and rho squared will be the transpose of these vectors. It will give you the contributions from S1, S2, S3 all squared. And then rho will look like this. It's quite simplified. So just by solving the eigenvalues and finding the invariant, you will directly have the point on the plane. You have J2 here, for example, and you have I1 used for the distance. So if you then take a pressure point like this, also I would say that this M here is connected to your local coordinate system. You see here, M is connected to your local coordinate system, which is on the plane, and the N vectors, normalized vectors, are connected to the global system. So if you take this point, Mi, consisting of these vectors, and you're knowing that because it's orthogonal, this N and I is an orthogonal plane, the scalar product will be 0. And this one will give you, for this system that you have here, you can find this relation. The P is the same as A divided by 2. And from that you can actually write out your Mi for unit vectors. And from this one you can put up this system. Rho cos theta is the same as this relation, M transpose, and this vector NP, which is the distance from the pressure point to your stress point in the plane. And you have this one already, and you know that this one we have already calculated. This is the principal deviatoric stresses, S1, S2, and S3. And you have this relation. If you calculate this one, you will have this one. And as I told you, theta is the angle in the deviatoric plane. And we calculated this one, that the distance in the plane is the same as 2 times the second invariant and the square root out of that, we can find that S2 plus S3 is the same as minus S1. We put that into this formula that we have calculated. We will find a relation for cos theta in the deviatoric plane. And this is a well-known equation, trigonometric equation. If we use this one, put this relation in, we will find that cos 3 theta will have this relation. And we take a look at this. Can we simplify this a little bit? S1 squared minus J2, and we can show that it is the same as S2 times S3. And we know that J3 is invariant. You can write this invariant like this. You can simplify this expression for cos 3 theta. And we know that now we have proven that this is an invariant, and the yield function f is the same as this one. And it's a simplified way. When you know this, you don't have to go through this one every time you have to calculate the stress condition. If you know this one here, you know that the first one will be the influence of the hydrostatic stress. The other one will be the influence of the deviatoric stress part, how large it is. But this cos 3 theta will be the influence of the direction in the deviatoric stress plane. This last one can be a bit tricky to know. I will go into that. What do we mean with that one? Because we have something called symmetry properties to simplify the equation. Yeah. The coordinate system. I got a question here where I got the coordinate system from. It's actually from the tensor properties we get it, because you have in tensor space you have the principal stresses, so it's like a theoretical invention. But then you need to prove that it's right, that you have it for material. You have to do experiments to prove that the theory is right. But in the mathematical theory, I will go into that now also. You can see that you have the symmetry properties, and from experimental evidence you can actually show that it's true, this property. So it's, yeah. Yeah, I will come. I will come to that. Yeah, I was talking about this direction here in the end, the yield function, and I got a question: how it's shown that is it proven that you have this property, and where do you get them from? So if you look at the last term here, I only say that it's the direction in the deviatoric stress plane, and if you build this up here, you have cos theta, and you look at the coordinate system. This is now the projected axis. This is in the local system. This is in the deviatoric plane that we're working now. And if you go around, because you have a polar coordinate system, you go into this different position. For example, this one, sigma 1, sigma 2, sigma 3. If you say that sigma 1 is always the largest one, sigma 2 is the second largest, and the sigma 3 is the lowest principal stress. If you go along this axis here, you will have tensile loading. Are you with me? Positive loading, so it will be tensile. But if I reverse it, so I go in this direction, I will be here, more or less, in this region. I will have compressive stresses on the sigma 1 axis. Are you understanding that or following me? So it's the same if I go sigma 3 here. This is tensile stresses, sigma 3. But if I'm in this area, I will have compressive sigma 3 principal stress. So you can have a combination of different kind of load cases here. So if you rotate, I'm first of all, I'm in this position. I have compressive part from the other two, and I have tensile from sigma 1 here. But if I move to this position, I will probably have some shearing properties, because I have, if I just rotate, we have a little slightly lower stresses from sigma 1, but I have contributions from sigma 2. So then I will have some kind of shearing. I will show you a little bit later with testing how it works. So I have to, if I rotate, I can find the same loading on my body here and here, because I'm just moved a little bit from one principal axis in stress space, sigma 1. I do the same at sigma 2. So I will find exactly the same loading at this position as I did in this one. And then I can say, okay, I have a periodic, the loading, 120 degrees, I have periodic loading. Also, I have symmetry. If I am at this axis, exactly at this point, then I move to this point here. And I compare it to this point. I just reverse it, the angle. Minus theta plus theta. I will have exactly the same loading. And also here, I can find that if I take the negative sigma 3 axis, this is this one. It will also be symmetric on both sides here, like that. So I have a lot of symmetries here, so I can simplify my equation quite much. Instead of taking the full principal stress coordinate system in the deviatoric plane, I can just slightly use 60 degrees of it. Any stress condition, stress state that I have in my loading, I can always relate to this 60 degrees, somewhere in this 60 degrees. And that's a quite good simplification. And it will simplify my equations and my models. Especially my models will be much simpler if I can use this criteria instead. So this is what it means, this slide here, that you have these symmetry conditions, and then you can simplify. And if you look at, because we call this load angle, this angle here is in between the 60 degrees and also the full one is called the load angle. It was proven by a researcher in 1920s or something about this criteria. And these load angles are always connected to the meridian plane, and I will show you that in the coming slide. But I told you that if we were on the first principal stress axis, sigma 1, and then we have this condition, we have tensile loading. We pull the material. Then we have tensile loading on my material. But if I pressurize it, I will reverse the load. Then I will have this condition, sigma 1, and will be exactly the same as sigma 2. And if I have shearing, pure shearing, I don't only shear the material. I don't push or pull anything. I just shear my property, my material. Then I will have something like this. I put a torque up here and have in the other way another torque, equally large. I will have this property that sigma 1 will be exactly the same as the torque and larger than sigma 2. So you have different kind of loading will be connected to where you are in this deviatoric plane, the local plane that you have projected. So depending on where I am, I will have different kind of loading. There. Yeah, you can. But this is for the theory that you should always, the largest principal stress should always be sigma 1. You always do that, independently if it's compression or if you reverse the load. The largest one is always sigma 1. And it's a good way of working with the modeling, it will simplify a lot. your model. If you just take that. Okay, so this is what I'm talking about more or less. You have the fluid angle 0. It's then the tensile meridian, where you have sigma 1 is the largest one. It's always larger than sigma 2. And this one is equal to sigma 3, because you're going in this direction here when you load it. And also this one, this can be your yield criteria for the whole model, this surface here. And if you have hardening, this surface will move or increase. We'll go into that later on. But if you're on this axis, you load the material, you reach your yield surface, your yield function. This is your, you will load the tensile meridian. This is what one will be the one that controls and actually limits your elastic part. Because inside this region it's elastic, outside it's plastic. So then you're loading on this one. If you have compressive, like you compress your material, you will go along this line instead. So you see, the distance here is larger than the distance on the tensile one. And this is usually true for all materials. That is less strength in tensile loading than in compressive loading. This is usually what you have. That's why you have this surface looks like this. So then you follow this one, then sigma 1 will be exactly the same as sigma 2, because if you look at this, this is the sigma 1 axis, this is the sigma 2 axis, and if you're in this position, they will be exactly the same and larger than sigma 3. And if you look at shearing, you will be in this position here, theta 30 degrees. So sigma 1 will be larger than sigma 2, and sigma 2 will be exactly the same as sigma 1 plus sigma 3 divided by 2. And you also have, I don't know if you can see it here, you have alpha 1, alpha 2, alpha half. I will come back to that on the next slide here, where you have this alpha. So you have, depending on how you load it, you will change the angle, and you will also change this alpha. So if we know this is your plane, you have rotated the coordinate system. You have this plane in stress space, and then you look from the side. You look at it from the side now. So then you have a line like this. This is the yield surface that you have. This is what you see in the picture here. And meridian, and you have a constant theta, so it stays on the same position all the time. And you also have arranged the principal stresses that sigma 1 is always larger than sigma 2 and sigma 3. You can actually write, for example, you can always write and connect your principal stresses in this way. So you have a connection. Sigma 2 is the same as 1 minus alpha times sigma 1 plus alpha times sigma 3. This is always valid, but you need to know your alpha and your theta. In this case, alpha. Then you can write, if you have this connection, because this is the stress tensor, how you connect the different parts, and this is the deviatoric principal stresses. Then you have S1, S2, and S3. With this alpha, if you know this alpha, you can always find your deviatoric stress. And you can find your cos theta with this relation. 1 plus alpha divided by 2 and square root out of alpha squared minus alpha plus 1. But this is only valid then for 0 to 60 degrees. And alpha 0 to 1. So this is a restriction now, because you know that you only need 60 degrees. Whatever loading condition you have, you can always, if you arrange your principal stresses like I told you, you can always use this relation to find the direction on this deviatoric plane. That's this one. Yes. Yeah. If you have, you see alpha tensile, alpha is 1, so it's there, and compressive, alpha is 0, there, and shearing, alpha is half. It's a mathematical model to find. No, it's just a construction. It's a normalized function from O to 1, and you use it. Alpha is very important because you connect it to this angle. You connect alpha to this angle here. You see here. If you know alpha, you know that okay, I have tensile. Then alpha is 1 in this. Look, if you look at this sigma 2 here, if you want to find sigma 2, you have a connect. You can always connect them in this way. Alpha is 1. This one will be 0, and this one will be 1. So it's the same as sigma 3. And S is the deviatoric part. If you know your alpha, you know what alpha, you know what kind of loading you have. And then you can always construct your deviatoric principal stresses. So that's what you use it for. So you have two coefficients that can vary. Yeah, alpha you can find. I got a question about alpha, how you can find it. And yeah, if you find your loading, if you find your load angle, you can find your alpha. But you need to do a lot of tests to really find this yield surface in different directions. It's not only tensile testing. You need to do compression, shearing, maybe biaxial testing, and so on to find. Yeah, so it's a lot of effort to really build this kind of model. For this, if the minimum test for the at least 3, I think 2 it will be a bad model, but 3 maybe you can have something good. So okay, some comments then. If you look at metals, for example, you don't have, as I told you in the beginning, you don't have any influence of the hydrostatic pressure. Some cases you can have, cast steel and so on, maybe you can have. But then we call it the convex trait in the deviatoric plane, because the yield stress, if this is tensile stresses, it will be the same on compressive stresses. You find it on both sides. But soil and concrete, rocks and so on, usually you don't have any yielding. You don't see the yielding. It's just elastic and failure. Usually what you see. And it's the influence from the hydrostatic stresses are very, very high. Also, if you have water content and so on, effective pressure, pore pressure and so on, it's even more complicated and so on. And then you usually need this cos 3 theta load angle dependency, depending on how accurate you want to build your model, of course. So then you say that you have a convex failure in the deviatoric plane. Instead of having, you know that you will yield the material when you reach the surface. You will fail the material instead. It will be you will break it. So I think it's time for a 5-minute break here. So okay. Okay, let's start again. I think actually this chapter is the key thing here is to know the coordinate system and how it works. Then you can relate all these models and all these things that you have in different kind of models to this coordinate system because it's built up from that one. And then it's better to understand the meaning and how it works, the model. So try to put some effort into the coordinate system, and then you have this is the key area in this chapter actually to know that one. Most of this chapter will be now to go through different kind of models and see how they work and so on. But the key thing is the coordinate system. Okay. Usually when you start with finite element modeling and plastic processes, especially metals, you have this. You get to know this model of von Mises, the von Mises criteria, and von Mises model. Now we have this coordinate system again, high Weirgard, and the principal stress space, sigma 1, sigma 2, sigma 3. And the von Mises criteria is more or less a cylinder in that stress space. I guess you have seen this picture before. And if we have this, it's pressure independent, as we say. And if we have the cylinder and we cut it off and put a plane here instead, then you just orient in this plane. This is what you do with this coordinate system, this simplification that you have. So you only work, if you have for one pressure point, it will be in this area here. And this is your deviatoric plane. It's also called the P-plane sometimes in the book. It's only a circle on a plane. And these are the projected axes, sigma 1, 2, and 3. And then you have your polar coordinate system with your theta. And you can see that the von Mises model is independent. If it's tensile, compressive, shearing, you will have the distance here from the middle of your plane to your surface will be the same, independent of any load angle. You don't need that one. If you look at this cylinder, it's straight. You don't have any that it's growing or something. So it's also hydrostatic, has no independence of hydrostatic pressure. The only thing that will affect this model is the deviatoric stress. And this is what you get here from the J2 invariant. This will give you the amount of deviatoric stress. And when you reach a certain amount, you will yield your material. This is when you reach the surface. This is yielding with the von Mises model. So it's the simplest one. And if you look at the meridian plane, you will have I1 theta, it will be the same as, you can put it as an invariant of J2 instead. You can also have von Mises stress on this axis, it's very typical to see. And as it's a straight line in principal stress space, this will be just one line. And if you later on in the course we will look at hardening, and the material will harden, you will only move this surface up. Then you will have hardening of the material, and then you need a function for that also. And you can do that in many ways. So we go into that in the next coming lecture. So you can write the von Mises model like this, J3, 2. This is actually square root out of 3 times J2 is the von Mises stress. I think you recognize that one. So this is your yield limit, sigma y0, the initial yield limit. If you put the function on this one, you will have hardening. When it's 0, you will start to yield. You can also write it like that with a normalized function. So when you reach one, when this is fulfilled, when it's actually 0, this one, you will have yielding. When it's more than that, you will have plasticity. If it's lower, you will be inside the circle. You have elastic material. This is one way of writing it. You can also write it with the principal stresses. This is also a very common way of looking at the model like this. You don't always have to look at stresses to find yield points and so on. You can also look at energy, strain energy, because when you deform something in any way, plastic or elastic, you will have strain energy. You can also divide, for the von Mises model, you can divide it into deviatoric strain energy and volumetric strain energy. And as we know, it's pressure insensible. The deviatoric strain will be the one that controls the plastic, or the yielding point. And you can rewrite it like this with the shear modulus and the deviatoric strain, or in this way with stresses. It's the same. Here you have the deviatoric stress tensor, and you have 1 divided by 4 times the shear modulus. or like this. And the volumetric part you can write with the bulk modulus and the deviatoric strain tensor. And at a certain value of deviatoric strains, you will have yielding. So it's another way of writing it. Before last lecture, we talked about different kind of conditions, like plane stress, plane strain, and so on. If you look at von Mises in plane stress, you don't have any stresses in the third direction. You see, sigma 3 will be 0. And you project that one. You take away one axis, and then you project it. You will have a lift like this. You have sigma 1, sigma 2, and here's a combination. So here you have a contribution from both sigma 1 and sigma 2. We can all write the model like this. You can see it's quite, you have the same properties all over the stress space here. Remember this picture when we look into the other models that come, because it's this one is symmetric, as you can see. Another condition is when you have this very, very thin-walled tube. It's almost like pure shearing, but you have very thin walls. You shear it, and you can also compress it, or you can have tensile loading, pull it. So you have tensile or compressive stresses. So this will be your stress tensor. Only one-dimensional normal stress, and then you have shear stress. The shear stress comes from the torque that you load it with. This one will give you the deviatoric stress tensor looking like this, because you take away the trace, you will have this part here coming on, but it will not affect the shear stresses. And you can write, for this type of simplification, you can write it even more simpler, like 2 times the normal component and 3 times the square root of the shear component. And you have a yield condition like that. And this is the orthogonal stresses. Can also be written like this, because it's another way of describing the model. This will be the yielding when you have, in this case, 0, you only have shearing component. This will be the criteria for yielding now. Tresca is another interesting model that in some cases actually is better than von Mises, even if it can be an old model. Here you have influence. Here, instead of having a circular cylinder, you here have edges like this. And if you look at it on this deviatoric plane, the P plane, you have something like this. This is a comparison also with von Mises, where you have a circle. And then you have the Tresca model, where you have straight lines. And here we can see that if you look at the tensile meridian and we look at the compressive one, it will be the same value. But the difference will be in shearing when you are in between here. Then you will have a lower strength of your material. And this can be true for some type of steels, I know. Then you will have a load dependency. Then you need to look at that one also for steel. And here you can see the difference. Compressive and tensile, and then you have a shearing. So when you look at these in this plane here, you will have a different yielding point for the material. And it's written like this: sigma 1 minus sigma 3 minus the yield condition here. And in plane stress, if you remember the von Mises model, here you have a square instead. It's still symmetric all over stress space for sigma 1 and sigma 2, but you have squares instead of an ellipse. So I think that looking at models in plane stress can be quite useful, because then you see maybe it's easier to understand instead of thinking 3-dimension stress. I think it's easier usually to look at it with plane stress, see where the sharing comes in and so on. But if you take the thin walled tube again, and we only look at shearing and one normal one normal term here, we'll have model looking like this, and it will be an ellipse exactly as for Mises, but you will have different values on the shear axis here. If you compare that one to the von Mises model, you will have another value, but it's still an ellipse. Even if in full stress space, it was this cylinder with straight walls. So this was more for steel material. If you then look into concrete, soil, and rock, we need to have some pressure dependency. And the first and the simplest maybe model that we have is the Drucker-Prager model, where we have instead of having a cylinder, we have a cone in principal stress space. And it's why it's looking like this is because you have the tensile part, and this material is very weak in tensile loading, and it's much stronger in compressive loading, so that's why it looks like this. The orientation of the cylinder looks like this. And octahedral criterion, you can have looking at the yielding in different kind of shearing components and in normal components. Then you can write it with this. It should be I1 here also, with invariance instead. So if you look at, we cut the plane. We have a circle. So we don't have any loaded dependency on the Drucker-Prager model. It will be like von Mises, but we have a pressure dependency. So we have a circle instead. So it will be constant, this meridian, if you look at that plane. And this point here and this point is usually something that you talk about when you have the Drucker-Prager model. Though. This beta here is more or less the cohesion of the material. You can relate it from tests and so on. Cohesion is when you have zero stress, you only have deviatoric stress. At that point, when you start to yield or you have failure in your material, this is cohesion of the material. This is for sand, gravels, and so on. Concrete can also make sometimes concrete. And this point here, beta divided by alpha, is triaxial tensile loading. So it's very difficult to find this property. Usually you need to have maybe a shearing test, or you can have Brazilian disc test or a uniaxial compression test to find that this angle of the model. And sometimes you can find it also in database depending on what kind of material you're looking for. You write it like this. You have 3 times J2, square root out of that, and you have alpha, I1, and minus beta. And beta was the cohesion, so that one you can take directly from the test. And alpha will give you the angle, how it's dependent on the pressure, because it's a straight line. So you can put this line from tests, or if you have done something else to find it. But you need this alpha and beta to put the model, to calibrate the model correctly. Do anyone know if I put alpha 0, what do I have then? We know that. Yes, we have the von Mises model, because this beta will be the yielding criteria then. We take away the pressure dependency if you take away alpha. Alpha is 0. So then it will be a straight line. There's a straight line here. So that's why I have alpha. So the Drucker-Prague criterion in plane stress. Now if you compare that one to the von Mises model, it's still an ellipse, exactly as we have, but you have moved it a little bit. And this is the tensile part, and this is the compressive part. And you can see that the material is much stronger in compression. You need to compress it much more than you have to put on tensile loading before you have yielding. This is what you can see directly from this plane stress model. And also here I just written out the formula. This is how you can write it with principal stresses. You have alpha, and it's affected by sigma 1, sigma 2, and you have your beta. But also this von Mises part here, you can write like this, in plane stress. You have something called also sigma T and sigma C. This is tensile stress, and this is compressive stress, and this is biaxial tensile stress and biaxial compressive stress. So this is the point. Biaxial is meaning that you have effects from two type of loading, sigma 1 and sigma 2. This is purely sigma 1. This is purely sigma 2. Those are the same. Sigma T, and it should be like that. But here you have a difference. Also you have compression, pure compression, and pure compression. But this is the biaxial compression test, which you can find the values you can put here in the model. So this is a way of calibrating. And if you know how to measure, you can calibrate this point for plane stress. So this one is pressure sensitive compared to von Mises, for example. And you can see what is happening when you have this pressure sensitivity. If you put away alpha, you will have a von Mises model. Then it will be exactly the same anywhere, everywhere in the stress space. But if you put the pressure component in, you will move this ellipse in stress space. So it's just a small change of the model, and then you have the pressure dependence. Another interesting one is the Coulomb criteria. And a general way of writing it is you use all the principal stresses, sigma 1, 2, 3, but usually this sigma 2 it's of no importance. So you usually have the largest and the smallest one. And then you can write this criteria. And this is the loading that you have. You have a material point, and you put shearing on it, and you put a normal component on it. So you work in 2 dimensions in this case. And one way of writing it is with this K times sigma 1 minus sigma 3 minus M. And K and M are then material parameters, so it's related to some test or something. And for uniaxial compression, it's a little bit simpler. Then you have your K, and then you have a value of your yielding in uniaxial compression. If you look at more circles, which is connected to this picture here also, you have a P, which is the position, which is the center of the circle, and you also have a radius of the circle. You can use this to combine the Coulomb criteria with the Morse criteria, and then you will have a little bit more advanced model, actually. But if you look at the linear model of this one, you have only an envelope here from the Coulomb criteria, which is straight, and you have these circles at different stress positions, and all these positions here would have different radius. And then you can construct this envelope, which will give you a full Coulomb model, a linear Coulomb model. And if you had this equation 1 and 2 that was on the other side here, that one, and also number 3 here, you can rewrite it into this form here. You can do it after the class maybe and look at the book. You can rewrite it into this form again. And to eliminate the first principal stress, you can have an expression of R with dependent on K and your compressive yielding. So this is the linear one, and it's what we call the shear strength dependent model. And you also have a cohesion point there. And usually this one is used for granular materials, so you need some kind of friction coefficient. You need to measure that one. So this is how you put it up. You have the cohesion and your friction coefficient and your stresses, and from that one you will find the connection to your shear part. And these are material parameters that is measured. But they tested this a long time ago, which they see that this model was maybe not the best one. So they put up a criteria, a nonlinear model, a more general model with the Moore column criteria. So it's a combination of the Moore and column where you have a nonlinear envelope here. So instead of putting exactly this linear relation that you had here, you just put an arbitrary function, h, which is dependent on the stress condition. And you take the tangents out of theta, which is the friction angle. And you know that if you can pressurize granular material at different points, low pressure, medium pressure, high pressure, you will have a nonlinear function, which can be this h, for example, here. And you have the differences will be, theta will be this one. And as you can see, at lower pressure we'll have one friction angle, and at higher pressure we'll have another friction angle. Then you can put it as a function instead and have this nonlinear envelope here. And then you write, if you know this one, you can have something called K, and K should always be 1 or larger than 1. And you have then, if you have this tangent, you can write it with sin theta, which is K minus 1 divided by K plus 1. And here you have this friction coefficient. You have a connection with this tangent phi. You can write it like this. It's well described in the book also. Then you have a new parameter called C here, which is the one-dimensional compressive limit divided by 2 times the square root out of K. And now, if you do this construction of your model, you can look at different loading types of the material. For example, going through the compressive meridian, where you have the same condition as before. Sigma 1 is exactly the same as sigma 2, but larger than sigma 3, and you have your angle 60 degrees. So your first invariant in compression now, if you have a compressive state, you don't pull the material, you compress it. We'll be looking like this. And also for the deviatoric second invariant, for the pressure state, you can write like this. But you know, you had an expression with sigma 1 and sigma 3. So then you can use that one. If you remember this equation that you have on the couple of slides before for the Coulomb model. If you rewrite this with invariant expressions instead, use this one, you will have something looking like this. It's more or less the same, but it's more generalized with invariant. This is the deviatoric part, and this is the pressure part. This is the limiting factor for uniaxial compression. If you put then K equal 1, you take away the hydrostatic part. It's like taking away alpha in the last model that we saw. This will be independent of the hydrostatic stresses. If you do then the same for this model with the tensile meridian, you have that sigma 1 is the largest one. It's always larger than sigma 2 and sigma 3. And this Lode angle is 0. You do exactly the same as you did for the compressive one. I've seen that it's a small error, it should be T here. You do exactly the same as you did with in the last model, in last thing. Then you can show for K equal 1 is also independent of hydrostatic stresses. It's a check. If you plot also this meridian in this plane, you will have a difference. You will have the compressive one will be stronger than the tensile one, and this we know already. But one thing that has to be exactly the same is this point where you both meridian meet each other. This one should be the same. And if you plot the trace of this one, you will have something that reminds you of the Tresca criteria with these straight lines here. But still you have, it's a cylinder in stress space. So you have a pressure-dependent cylinder. But here you can see the difference between Tresca and this one. That Tresca, you have the same strength for tension and compression. This one will have a lower strength for tension than compression. But it will be conical, so you have it will be weak for tension and strong for compression. And this is how it looks like. And you have this rho that we were talking about in the beginning for the Haig-Westergaard coordinate system. When you take the deviatoric plane and the slice of that one, you have the angle and you have the distance. The distance for the compressive part will be rho C, which is the distance from origo to this point here, and rho T will be the distance from 0 to the tensile limit, tensile yielding. And if you divide this one by rho C and rho T, you will have this expression here. And this is the Mohr-Coulomb model. If you look at this one for, maybe this is, if you have looked at models, you can, this is one way of expression, the Mohr-Coulomb model in plane stress. It will be a square, and you have this is the biaxial tension, biaxial compression, tension, compression. And it's, as you saw with the Drucker-Prager model, it's weak in tension, strong in compression. But it's with a difference here that you will have also quite large difference. You can actually control the behavior for tension and compression much better with this model, because the other one doesn't matter how you rotated it, the model. It was just a pressure sensitive. This one will also be sensitive on the Lode angle in that sense. And something about the rest of the chapter here. We have the 4-parameter model. It's the logic is the same as for the other ones that you have, that I've been going through. You have dependent on different kind of invariants and so on. So take a look at these ones. Also take a look at the anisotropic part and how yielding is connected to anisotropy, because then you have different properties in different directions. That's the difference. The other ones that we have looked at now is just isotropic ones. And this week I will put up a new assignment for you also that will cover then until this chapter more or less. And we will meet, I think it's in a month or something. It's the 25th or something, we'll meet again. And I will put a deadline around that date, maybe just after. So if you will have some questions or something, you can ask me. How is it going? You have started with the first assignment. I see that some of you anyway have send me some reports anyway. So if you have any problem, you can ask me or discuss with your classmates here. If you don't have any question, I see you next time. Then it will be a month's break now. I think you need it to do all the assignments and the reading. It's a lot of reading now, especially in the beginning here. So quite many pages to cover. So okay, I'll see you then. Yeah, yeah.